Let's say you were able to view the Earth's movement around the sun and also the sun's movement relative to the Earth at the same time. This is what you would see. So if you could stand on Earth and in space at the same time, which you can't, this is what you could hypothetically see. But this is basically what is happening throughout the months. And so if you were able to condense an entire year's worth of time into 3 seconds, you would see that the sun sort of bobs up and down, and it reaches its lowest point in December, which is the solstice. It reaches a midpoint in March, which is the equinox. It reaches its height in June, which is the summer solstice, and it goes back into a midpoint on the autumn equinox and then returns. So what you're seeing is not really the sun moving so much as the Earth's tilt. And as the Earth is tilted 23 degrees kind of permanently, it's the orientation of the Earth relative to the sun that either provides more sunlight or less sunlight. So what this animation is demonstrating is the sun's position on any morning of the month throughout a year condensed to 3 seconds time. And what you would effectively observe is the sun's movement sort of bobbing up towards the northeast, down to the southeast. And at that midpoint is the equinox, the high point is the solstice of summer, and the low point is the solstice of winter. Also animated here is Jupiter from the perspective of Earth. And as you can see, compared to the sun, Jupiter moves from east to west, and the sun kind of stays in the eastern locale. After centuries of observation, many of the ancients and people like Copernicus, people like Galileo started to realize that this object in the sky was not a star because it did not move quite as fast. And what they confirmed was the speed of the stars was not the speed of the stars itself, but the speed of the Earth. And what they were seeing was not the stars moving, but the Earth moving. And they noticed that this object was moving slower than the stars, not because it was further away from us than the stars is, it was actually closer to us than the stars are. In other words, if you're trying to track Jupiter's counterclockwise movement throughout a month, it is much more difficult because at the same time every morning, you will notice that Jupiter has moved clockwise in the sky. But this is not because Jupiter has actually moved clockwise around the sun, relative to the northern hemisphere that is, but it is because the Earth has moved counterclockwise around the sun faster than Jupiter. It is easier to track Jupiter's counterclockwise motion throughout a year because throughout a year, Jupiter will have gone through one zodiacal background constellation by about 30 degrees from the west to the east. To put this in a clearer perspective, in June of 2024, Jupiter was on the Aries-Taurus cusp, and in June of 2025, if we're still around, Jupiter will be on the Taurus-Gemini cusp, and so it will therefore have traveled from the west to the east, thus proving counterclockwise motion. Now, if you're standing in the southern hemisphere, you're standing upside down, and the Earth is actually tilted away from the sun during July, and it's tilted towards the sun in December. So the seasons are backwards. So in June, you got winter, and December, you got summer. And if you can observe Jupiter once again, Jupiter, instead of going clockwise in the sky, it's going counterclockwise relative to the clockwise motion of the Earth relative to the southern hemisphere. And so what we're seeing is the sky turning counterclockwise as well as the zodiac. So the sun is going to rise on the opposite side of where you would be accustomed to seeing it rise. So if you woke up in Australia, in Sydney, Australia in this case, you would probably be confused as to seeing the sun rising on the opposite side. Also take note that Jupiter, instead of moving throughout a year in a counterclockwise motion as it would in the northern hemisphere, it has now moved in a clockwise motion from the Aries-Taurus cusp to the Taurus-Gemini cusp. And if you were able to see the movement of the Earth in both directions from both different places, this is probably what it would look like.